In this video on section 7.1, we're going to learn how to find area of regions enclosed by curves and the length of an arc over an interval by using definite integrals. We will derive the formulas so that it will help you remember them actually. So let's just draw a picture of maybe y equals f of x and y equals g of x. So let's say this is g and this is f. So we want to find the area enclosed by the curves f of x and g of x. So of course at first we would need, if this were an actual problem, if the intersection points were not given to you, you would have to solve f of x equals g of x and find a and b. Find the intersection points. Now, what we're going to do, but I'm not going to do it all out in great detail. You can look at the book, and he also explains this in maybe slightly more detail than I will here. We're going to partition the interval AB into a regular partition of length n. In other words, n equal subintervals of width delta x. And I'm just going to draw the ith subinterval right here. And this is x sub I minus 1, and this is x sub I. But I'm not really going to need those, so let's not clutter up the drawing. I will pick a arbitrary c sub I in anywhere I want. It could be left endpoint, right endpoint, midpoint, or throw a dart and get it, because we're going to let n go to infinity, and it makes no difference. These little rectangles are going to be so thin. And I'm going to use that c sub I to go up and get a point on G and the point on F, and I will use those heights to get the size of my rectangle within the region. So we have a rectangle lying over the ith subinterval, and of course we have n of these rectangles, but we're just going to call this rectangle a representative rectangle. So its width, of course, is delta x, and its length or height will be y on the top minus y on the bottom, which was determined by choosing c sub I. Let's call the area of that little rectangle delta a sub I, a little piece of area lying over the ith subinterval, the area of the ith rectangle. And I'm going to write it all out. It's going to be, well, let's put y on the top minus y on the bottom, a vertical distance, and delta x we know is its width, which is b minus a over n. But y on the top is f of c sub I, and y on the bottom is g of c sub I times delta x. So what we see here is the area of the ith rectangle written in terms of the functions f and g, and just c sub I chosen in the ith subinterval. So we could say then that the area, if we add them all up, the area, which is the sum of all these quantities, I'll go ahead and write it, f of c sub I minus g of c sub I delta x from I equals 1 to n, that A is approximately equal to that, the area of the region. And what is this? Well, you should recognize this as a Riemann sum. It's a Riemann sum for the function f minus g. So we have then that the area is equal to the limit of that Riemann sum as n goes to infinity, or the integral from a to b of f of x minus g of x dx. and that is your formula for finding the area enclosed by two curves where one is always on the top and one is always on the bottom. Now, of course, you're not going to go through that derivation every time, but it's interesting to see how in this application we develop a Riemann sum by partitioning and looking at areas of tiny little rectangles that approximate the area over the ith subinterval. The way I like to think of it, and I don't memorize formulas like that, I think, well, a little differential of area would be the area of a representative rectangle. And I just think of this as a representative rectangle here. And I don't write C sub I or anything. I just imagine it to be at x. So then I would think of that as just x. And I would think, well, the length of that little sliver is f of x minus g of x. And the width of it, delta x, well, delta x is the same thing as dx. So you can see why I call this a differential of area, because we have already proven over here that the area is the integral of it. Well, the area is the integral of the differential of area. So it is exactly what we have here. So I'm going to use this idea as I do some examples, and you if you prefer just to memorize a formula, that's okay, but we don't have to memorize the area of a little sliver of a rectangle. We all know that, so it might be easier to do it that way. So our first example will be finding the area of the region enclosed by y equals x and y equals x squared. If you draw the line y equals x and y equals x squared, you see that the only region enclosed by them is in quadrant 1. And the intersection point is easy to find. Setting x squared equal to x, you get 0 and 1. And so I've graphed it here for you. Now, here's what I do. I say, okay, I want to draw a representative rectangle. So what do I mean by a representative rectangle? So let me draw one here. Just anywhere I draw, listen really carefully here, anywhere I draw a little rectangle. If I draw it vertical like that, if I drew it here, the top would be on the line and the bottom would be on the parabola. If I drew it here, the top would be on the line, the bottom would be on the parabola. No matter where I chose x in the interval 0, 1, no matter where I chose x in the interval 0, 1, my rectangle, my vertical rectangle would have its top on the line and its bottom on the parabola. That's why we call it a representative rectangle. No matter where I draw it, it will have the same formula for its area. So I'm going to call dA the area of the little rectangle, and it's going to be length times width, y on the top minus y on the bottom, since it's vertical, times dx. dx is the same as delta x. And that is y on the top. Well, we want to put everything in terms of x, don't we? Because we'll be integrating in terms of x. So I need y on the top is x, and y on the bottom is x squared times dx. That's my differential of area. My area is the integral of dA, which is the integral from 0 to 1 of x minus x squared dx, and let's see, 1/2 x squared minus 1/3 x cubed. Between 1 and 0 gives me 1/2 minus 1/3 is 1/6. So let me draw another region that we can try to find the area of. And this time it'll look a little bit different. This time, let's see, this is minus 1, that would be 6. This is the point 6, 3. Now remember, in your problems, you may have to solve for points of intersection, but I'm giving them to you here. And that may not be, oh geez, that's so bad. I can't draw a straight line. Okay, sorry about that. I tried to fix it. It's hard to draw on this bamboo tablet. So let me give you the equations here. This equation of the parabola opening to the right is x is equal to y squared minus 3, and this straight line, ho-ho, is x equals 2y. It's not really, doesn't look too straight, but the problem is to find the area of the region enclosed by the curves x equals 2y and x equals y squared minus 3. So if you set 2y equal to y squared minus 3, you'll quickly get y equals minus 1, y equals 3. So then you solve for x and get the points of intersection. Now this time, let's think about that representative rectangle. We're always going to find area only if we can choose a representative rectangle and imagine that partition, summing over the partition, taking the limit as n goes to infinity. If I draw a rectangle here, and I'm going to erase it after I do it, but if I drew my representative rectangle, if I just chose x right there, that's fine. Y on the top, we'd have to solve for y, wouldn't we? And y on the bottom. But notice if I drew it over here, it would not have the same formula for its area. Y on the top would be on the top branch of the parabola. Y on the bottom would not be on the line, it would be on the bottom branch of the parabola. So this is not the ideal way to try to do it. We could integrate from, this is minus 3 here, to minus 2, and have to figure out the area of that one, and then integrate from minus 2 on out to 6 with y on the top minus y on the bottom, but still we'd have to take the positive square root of x plus 3. So let me erase these two rectangles and show you, that should be erasing. I guess I have to stop it. Instead of drawing a vertical rectangle, notice if I draw a horizontal rectangle at any value of y, if I draw a little horizontal rectangle, and I'm just picking an arbitrary y there, y between negative 1 and 3, y between negative 1 and 3, then any rectangle that I draw will have, watch, if I draw it here, its right end point is on the line, its left end is on the parabola. If I draw it up here, its right end is on the line, its left end is on the parabola. So we could call this a representative rectangle, and its width is dy, its thickness is dy, and its length is x on the right minus x on the left. So let me write that. dA, the differential of area, will be, well, it's going to be x on the right minus x on the left times dy, and we'll integrate with respect to y. Well, x on the left is 2y. We need everything in terms of y because we're going to integrate in terms of y. Minus x on the left, well, that's solved for, y squared minus 3 dy. That is the area of the representative rectangle. And of course, the area is the integral of the differential of area, which is the integral of 2y minus y squared plus 3 dy. And, well, we can go ahead and evaluate that, but I'm going to leave that up to you. It's going to be the integral from minus 1 to 3. So you just integrate and evaluate between 3 and negative 1, and you have the area. I got 10 and 2/3 after you integrate, find the antiderivative, and evaluate between 3 and negative 1. Now he gives you the area formulas on page 416. You might want to write those into your notes, and if you want to memorize those formulas, that's fine. They'll work, but you have to be able to judge whether or not you can integrate with respect to x or with respect to y. And I always do that by asking myself, will a vertical rectangle always have its top and bottom on the same curve, no matter where I draw it in the interval? Or will a horizontal rectangle always have its right end and left end on the same curve, no matter where I draw it in the interval on the y-axis? You have to decide which formula you want to use. The author does 2 or 3 more examples for you, which you should see. The regions are drawn on page 415, and he calculates the areas in example 4. So take a look at those. Try to do them yourself. Turn to page 415 and try to calculate the areas of the 2 regions in figure 4. So that's figure 4 on page 415. You can't see his solution there, so you try to get it, and then just turn the page, and the solutions are in example 4. So that would be a great exercise for you, and if you can calculate those 2 areas on your own, then you're ready for the quiz, and you can check your answers with example 4. So now we're going to move on and show how to measure arc length using definite integrals. So here's a picture of a graph drawn over an interval AB, and we're trying to find the arc length. So let's state the problem. Find the length of the curve y equals f of x over the interval AB. Well, again, we're going to partition, and I'll do the partition this time so you can imagine what we're going to do. We're going to partition the interval. Here's our ith interval, let's say. We're going to partition it, and at each, we're not choosing a c sub I. At each endpoint, we're going to go up and grab the point on the curve. And so we're going to get a bunch of points like this. On the ith, let's call this the ith, let's call that x sub I, and no, x sub I minus 1, and this x sub I, we'll make it the ith subinterval. We get these 2 points, and we keep going, and finally we have this one. Now what we're going to do is we want arc length here, so we are going to make a partition and then just draw the straight lines between these 2 points. And so we're going to estimate the arc length by adding up the line segments. It's a polygonal curve that we're going to figure out easily by just adding the distance between those points, and you can see how it would be a good estimate to the arc length. So what we need is to find out how do we express the distance between those 2 points, the length of that segment, on the ith subinterval, and then we just add them up, I equals 1 to n. And hopefully we'll have a Riemann sum, and thus a definite integral. So let's see, I need to label the points. This point here on the right is x sub I, f of x sub I, and the point on the left is x sub I minus 1, comma, f of x sub I minus 1. So we have our 2 points, and let's just use our distance formula. So we're going to find the length of the little line segment, estimating the length of the curve over just the ith subinterval. So it's going to be the square root of, using our distance formula, f of xi minus f of x sub I minus 1 squared, y1 minus y2 squared, plus x1 minus x2 squared, in other words, x sub I minus x sub I minus 1 squared. That's the distance between those 2 points. But now, if we just add these up, that's not a Riemann sum, because we have both x sub I and x sub I minus 1. We have to get it as a function of some c sub I in each interval one at a time. So let's just do some calculating here, and I think you're going to see something that will surprise you. I'm going to take this perfect square, and I am going to divide it, I'm going to factor it out of both of these terms. So I would get f of x sub I minus f of x sub I minus 1 squared, divided by, I'm going to factor it out of there, so I have to put it in the denominator, x sub I minus x sub I minus 1 squared, plus, now I'm factoring it out of here, 1. Now, under the square root, I would have all of this times, well, I'm going to put it there, just so you see the algebra. I would factor it out, and I would have it right here, x sub I minus x sub I minus 1 squared. So all I did was I took that quantity and factored that perfect square out. And now the square root of the square root of a times b is the square root of a times the square root of b. So I can take the square root of this, it's a perfect square. And xi minus xi minus 1 we know is positive because xi is to the right of xi minus 1. So the square root of that is very easy to take. We don't need absolute value signs, and I think I'll make the inside look slightly different. F of xi minus f of x sub I minus 1 over xi minus xi minus 1 plus 1. That was squared. Plus 1. And now out here I can just take the square root, and I have xi minus xi minus 1. Well, now we can look at this carefully here. Xi minus xi minus 1, we know it's a regular partition. That's just delta x. So, and what is this? What does this remind you of something here? Just take a look at it before I tell you. If you took the limit of f of x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1, as x sub I minus 1 got closer and closer to f of xi, what is that? Hopefully you said, oh, that would be f prime of xi, because that's just a difference quotient. So I'm going to say this is approximately equal to, I guess I'll go back to green, this is approximately equal to the square root of f prime of xi. As xi minus 1 gets closer and closer to xi, this is just the difference quotient, which would in the limit become f prime of x sub I. So if n is really, really big, this is almost equal to f prime of x sub I squared plus 1 times delta x. Now, if we were to add this up, now if we write summation I equals 1 to n of the square root of f prime of xi, quantity squared, plus 1 delta x, then what this really is a right Riemann sum. We're picking the x sub I in each subinterval, taking the derivative, squaring it, and our function is then the square root of f prime of x squared plus 1. This is a Riemann sum. So as n goes to infinity, the limit of this as n goes to infinity is equal to the integral from a to b of the square root of f prime of x squared plus 1 dx. So that's the formula that you are given in the book, and that is the length of the curve from A to B. We could say this is equal to L, the length of the curve. So that's just a formula. Now you can memorize it if you want. Actually, it probably would be a good idea because you don't want to derive that every single time. But look through the derivation. It's really neat how that comes out to be a Riemann sum. And the minute you estimate a quantity, some measurement in science, if you can estimate with a Riemann sum, then you know that you can exactly calculate with a definite integral. So here's an example. Let's write the formula down again. L is equal to the integral from a to b of the square root of f prime of x squared plus 1 dx. So here we want to find the length of the curve y equals x to the 3 halves from x equals 0 to x equals 4. So I would take a look at it, and you see your curve here, and it's 4, 8. And so we want to calculate. So let's first of all take our derivative. F prime of x is equal to 3 halves x to the 1 half. So f prime of x squared, I'll just square it right here, will be equal to that, which is 9/4. X to the 1 half squared is x. So our length here is going to be the integral from 0 to 4, x equals 0 to x equals 4, of the square root of 9/4 x plus 1 dx. So this would be a simple substitution. I don't even think I'm going to leave x and have to change my limits of integration. I'll keep it 0 to 4. You could do a u substitution and change the limits. Why don't you try it and see if we get the same thing? We have 9/4 x plus 1 to the 1 half. I have dx here, but if u was 9/4 x plus 1, then du is 9/4 dx. So I need 9/4 and on the outside 4/9. And now I see I have here, this is u to the 1 half, and this is du. But I'm not going to leave x. I'm just going to integrate directly. So I have 4/9, and I will have u to the 3 halves, so 9/4 x plus 1 to the 3 halves, and I needed 2/3 here. And I would evaluate between x equals 4 and x equals 1. So let's see, what's that? 8/27 times, and now plugging in 4, I have 9 plus 1 is 10, so that's 10 to the 3 halves, minus, plugging in 0, I have 1 to any power is 1. So that is my answer, and I think on a calculator you'll get about 9.1 units, whatever the units of measurement were of length. The arc length formula is on page 419, and I think this was an example in the textbook that I just did. So I think most students find this to be pretty easy, as long as you can find the intersection points and calculate the derivative and everything. So that's it.